Kevin Nelson will be setting up our next presentation here for us.
Good afternoon, folks. Running for the home stretch this afternoon. So here we have a very interesting industrial vision systems project. Covered a lot of interesting different engineering technologies along the way. So it's my distinct pleasure to introduce Mr. Chris Lasher. Chris, take it away.
Thank you. For my senior design project, I completed design work in order to install a vision system at Berry Plastics. Mr. Nelson was my faculty advisor, and at Berry Plastics, I worked with Mr. Brian Margent and Blake Kinter. The objective of this project was to complete all pre-implementation work for the installation of a vision system that had various defects on an extruded sheet of plastic. As I said, Berry Plastics is a sponsor for this project, and Berry Plastics is a global leading manufacturer of value-added products. The headquarters for Berry Plastics is in Evansville, Indiana. In the Evansville facility, there is over 2,000 people employed and over 25,000 people employed worldwide. In 1998, Berry Plastics added a new thermoforming department in its Evansville plant. Thermoforming is a new and more profitable way of making plastic products. Currently, the Evansville facility has 23 thermoforming lines. The thermoforming process is pretty long and complex. This diagram shown here is a simplified version of the processes that is included in this project. There are several more processes that are included after step 5. To begin, resin or small particles of plastic are added to an extruder. In the extruder, the resin is melted and is forced out of the extruder through the portion of the extruder called the die. When the plastic is extruded, it is in the form of a flat, long, wide piece of plastic. The giant rollers after the extruder further flattens the sheet to specified thickness. Then the plastic enters the oven. The oven heats the plastic so that the plastic becomes more malleable. The malleable plastic then enters the thermoformer. In the thermoformer, a mold presses onto the sheet and forms the plastic product. Once formed, in the thermoformer, a trim press trims out the parts, and the parts are passed on to the operators. One of the lines in the Evansville facility is TFE 11, thermoforming Evansville line 11. Since this line began production, several sheet defects have proved troublesome. The sheet defects occur during the extrusion process. The first defect is the hole defect. This defect occurs whenever a foreign substance is added to the extruder with the resin. Whenever the foreign substance reaches the die of the extruder, the flow of material is temporarily halted, causing a hole in the sheet. This hole will ruin the structural integrity of the product form. The next defect is called the line defect. This defect occurs when there is a buildup of plastic on the outside of the die. The buildup on the outside of the die scratches the plastic as it is extruded. Although the structural integrity is not compromised, this defect is visually unpleasant and will not be sold to a customer. Whenever the buildup on the die breaks free, it is extruded with the plastic. And when the roll stand, if the buildup is large enough, the roll stand will not be able to flatten the buildup of plastic into the sheet. Therefore, there will be an uneven distribution of plastic. This uneven distribution, when formed into parts, will ruin the structural integrity of the product. Ultimately, the defective parts cannot be sold to the customer. Therefore, the time and money used to make the defects are wasted. A vision system is added between the extruder and the thermoformer, and these defects can be spotted immediately, and the corrections can be made so the defects are no longer formed. In order for a vision system to be functional and meet our purposes, several requirements need to be met. First off, the vision system needed to spot the hole, the line, and the diagonal defect. Second, the vision system shall be installed between the extruder and the thermoformer. And third, the vision system shall be able to process the images of the sheet faster than the maximum extrusion speed. In order to complete the design of the vision system, the vision system of the entire vision system, a vision system had to be selected. A location for the vision system had to be selected. And a mechanical design had to be completed in order to mount the vision system. And maintenance of the lens and cameras, design for the maintenance of the lens and cameras had to be completed, as well as electrical power design. And once the design was complete, economic justification had to be performed in order to get the project funded. There are two main types of vision systems that are used. One is an area scan, and the other is a line scan system. Based on how the line scan system records its images, the line scan system was chosen for this project. The line scan system will be used so that the entire width of the plastic sheet will be recorded one row at a time. Then the rows will be compiled into an image. Once the image is complete, the image processing will search the images for defects. Once it was determined that the line scan system was going to be used, vendors were contacted. The first vendor was Teledyne DASA. A representative from Teledyne DASA met with me and fellow employees who gave an introduction to the line scan system that they sell. At the end of the meeting, the representative was given several defective sheets, and the representative took those defects back to his lab and compiled a test report. The second vendor was Keenan's Corporation. Keenan sent a representative with an actual demo case. A demo case was set up and recorded the defects, and using image processing tools, the defects were able to be spotted. The representative also was given defect samples so that he could compile a test report so that could be reviewed at a later date. When both test reports were received, they were analyzed. Teledyne DASA's report proved that the cameras could spot the defects with proper lighting. However, image processing tools were not used in order to prove that the defects could be spotted as actual defects. Keenan's Corporation not only proved that the images could be collected clearly, but it also did prove that image processing could detect defects. Ultimately, Keenan's was chosen as the preferred vendor. Keenan's was chosen because the test report proved that the system could detect all defects, and based on specifications that were given by Keenan's, we were able to calculate that the maximum extrusion speed, but that the vision system could process the images of the sheet faster than the maximum extrusion speed. Next was to determine the location of the system. The system is going to be installed on the end feed to the oven. This location was chosen because not only is it between the extruder and the thermoformer, but at this location the sheet is flat and hot, which provides a smooth surface for the cameras to collect the images of the sheet. Also, above and below the oven end feed is strip room to add the mounting unit for the vision system. And here is back on the diagram. This is where the system got it. It is simply on the entrance point to the oven. On your right, on your left, sorry, is a 3D model of the current oven end feed. At the top and bottom of the end feed is a flat stainless steel plate. The two plates at the top and bottom serve as the outer frame of the current oven end feed. The cameras will need to be mounted below the sheet in order to spot defects. Because of this, slits will need to be cut into the oven end feed. There will be two inspection stations, therefore 2 slits will need to be cut. Then, in order to reinforce the oven end feed, between the top and the bottom plate will be added another piece of stainless steel that will help support the top and bottom plates. And on your right is a 3D model of a modified oven end feed. Now, since the location was determined, the mounting unit could be built. The requirements for the mounting unit is that the mounting unit shall be enclosed in order to help protect all components and help keep the light from the line lights focused onto the sheet. Also, the camera shall be protected by metal guarding. Air shall be blasted above and directly parallel to the lens to help keep the lenses clean. And the camera shall have 3 degrees of translational freedom and be able to pivot parallel to the motion of the sheet. The design of the mounting unit was based off the location of the sheet line. From the sheet line, using manufacturer specifications for focal length and light intensity, the cameras and line lights were positioned. Then, based off the position of the line lights and cameras, a mounting frame was built. So Kia is the provider of the cameras, has a table that you can choose your focal length based on your target size. For this project, the target is a flat piece of plastic. Depending on what product is made, the maximum width of the sheet of plastic will be 39 inches. Therefore, the cameras need to be at least 22 inches away from the sheet. And that 22 inches is the number that I gathered from the table provided by Kids. This here is a picture showing the third distance for the line lights. The line lights light intensity will be, for the proper light intensity, the line lights need to be 3.5 to 10 inches away from the sheet of plastic. Using these specifications, a rectangular mounting frame was built. This mounting frame will be positioned around the oven end feed. There will be enough room above the oven end feed to add a line light 4 inches above the sheet, and enough room below the oven end feed to add a camera that is more, that will have about 25 inches of room below the sheet, so there's plenty of room for the cameras to move. The mounting unit is made out of T-slotted extruded aluminum. Several attachments can be added to the extruded aluminum. For instance, a linear bearing shown in the bottom left of the slide. The linear bearings will be added to the vertical beams of the mounting frame. And connecting the linear bearings will be another piece of extruded aluminum. And on the horizontal piece of extruded aluminum will be another linear bearing. Therefore, anything attached to the horizontal linear bearing will have 2 degrees of translational freedom. Then attached to the horizontal linear bearings will be a steel tube. And on the steel tube will be a aluminum mounting plate. This mounting plate can be loosened and retightened. When loose, the aluminum plate can slide and rotate freely across the steel tube so that it can be positioned wherever it is desired. Therefore, the total assembly, in order to have provided 2 cameras with all 3 degrees of translational freedom and the ability to rotate and motion of plastic, linear bearings, and the aluminum plating will be used. On the aluminum plating will be the cameras. As said, the camera shall be protected by a steel frame. The camera will be simply put into the steel frame that will be bolted to the aluminum plate. Now, the line lights need to be able to rotate parallel with the motion of the sheet. Therefore, a 180-degree pivot mount will be bolted to the frame of the mounting unit on both sides of the mounting unit. And connecting the 2 180-degree frames will be another extruded piece of aluminum. Bolted to that piece of aluminum will be the line lights. Therefore, if you rotate the handle on the 180-degree pivot mount, you will rotate the aluminum beam, which will in turn rotate the line light. Here's a SolidWorks model of the entire inner frame design that provides the camera and line light proper motion. The oven end beam will be in between the 2 line lights. In order to help maintain the cameras, air will be sprayed directly above and parallel to the lens. Air will be supplied from current air lines in the facility. From those air lines, and a quarter-inch air hose will be fed to the air nozzle that will spray air flat and across the power supply provided by Keyence is a 24-volt 6-amp DC power supply. However, the line lights is provided by a different vendor. The line lights require a 9.9 amperage draw. Therefore, the power supply provided by Keyence will not be purchased since it will not be able to provide the proper power to the line lights. At that time, I investigated and looked at manufacturing specifications for several power supplies, and I found a 24-volt 40-amp DC power supply was found, and this power supply will be purchased and will be used to properly supply the entire system with power. It is projected that this project would cost about $43,000, and this includes the cost of the vision system, line lights, power supply, air equipment, and the mounting unit. Based on standards for going into line 11, it costs about $874 to run the line for 1 hour, and within 1 hour, 168,000 parts can be poured. And it's estimated that per year, about 5 million parts are defective due to these sheet defects. Therefore, it is calculated that it would take about a little under 30 hours in order to manufacture the 5 million parts, with a remake cost based on the cost to run the line per hour to be a little over $26,000. The implementation cost, as I said, was just over $43,000, which resulted in a payback period of about 20 months. So a vision system was selected, a location was selected, and a mounting unit for the vision system was designed. Then controlled air was utilized to help protect the camera lens. A power design was completed in order to provide proper power to all the components of the vision system. And then ultimately, the economic justification was performed, which led to a 20-month payback period. Currently, this design needs to be presented to the Illinois Engineering Management. Then, the management will decide whether to fund the project or not. If funded, materials will be purchased, and the assembly will be made and built in-house. Questions?
Questions? So, Chris, could you go back to the camera mounting system there? We showed, I guess there were 2 cameras, and the lighting and the fixture, and like that right there. So, can you talk to us about the cameras? Are they fixed?
But they will be fixed to the aluminum plate that's right there. And then the aluminum plate will be able to be loosened and rotated so that whenever different products are made, the width of the sheet changes, so the cameras will be closer to the lens or closer to the sheet. So it'll be fixed to the aluminum plate, which can rotate the slide across the steel tube, and the steel tube is attached to the bearings, which provide 2-1-3 translation to help properly put the lens in the desired location.
And where is the product with respect to?
The product will be in between the 2 line lights.
I'm trying to follow this here. The product is where?
The product, there's about 10 inches between each of the bottom and top of these 2 line lights.
Okay.
And in between the 2 line lights will be the oven feed, and on top of the oven feed is the sheet. And the plastic sheet is continuously flowing on top of the oven feed. And cameras will be underneath the sheet.
Okay, so the cameras are underneath the sheet. And when Keyence did their demo, what kind of was the setup that they had as they did their demo to do their proof of their concept there?
That was done on a tabletop with, they had demo days with similar cameras. They had a line light, and how you did it was you pushed the sheet along an encoder, which would time how much sheet went past in order to help the cameras record images of the sheet. And that's how the images were compiled. And then a flow chart or image processing was built so that different filters were applied
So, but was the testing done on the actual line here? or-
No, that would, in order to do, that was not in the scope of the project. That was this entire design just to test that, in order to test that method. It was just, the defects were cut out of the sheet, like current, like actual already extruded defects were cut, put on a table, split underneath the camera in order to collect the images.
You've demonstrated that the image system will detect a defect. What is it supposed to, what else is supposed to happen when it makes that detection? Is it supposed to decide to not make a part or ring a bell or what?
Yeah, from the vision system, the signal will be sent to the thermoformer, and so whenever the signal is sent, it will say, and 30 feet of plastic that goes underneath through the thermoformer, stop forming parts, so that the defects do not get formed into parts. So that after the thermoformer is a grinder that grinds up the plastic, so that the plastic can come back in.
Okay, and then also, I'm curious why a company that makes the vision system does not also supply the lights? Why you had to buy those from a different company?
I'm sure we talked about that, and they were on partnering with a company called Metaphase. But that partnership never went through, so.
Thank you.
I'm kind of curious, what type of lights, what type of lights are there?
They are, 45 inches long, they're just high intensity lines. I haven't.
Because it looked 24 volts by 10 amps doesn't get you a lot of wattage. Does it? Or am I calculating something wrong? No, the supply was 40 amps. What they were drawing was 9.9. It's just not a lot of wattage for a really intense light.
Well, maybe I might need to look further into that.
Okay.
Maybe my calculations are wrong.
And then another is, if they did their testing offline, how do you know the vision system will work when that line's running at full speed?
The specifications came with the cameras, and that it could, the frame rate was given, and then from there, the pixel size was used and converted into inches of the sheet, and then it was calculated that about 500 feet of plastic could be processed in a minute, and if the extruder extrudes a sheet at about 250 feet. So based off of frame rate.
So you hit the Nyquist sample rate at that point.
Any other questions? All right, let's give him a hand.